Uh, our today's lecture will again be related to the work done that we started last time in the last recorded video, where we discussed about work done in a process and how we can estimate it from the PV graph. So today we are going to further elaborate on different kinds of work. So the general definition of work is what is we learned last time. So general definition of work is something, some product of pressure and change in volume. So that is the D means very small or incremental work. D means very small or incremental work. So we call it infinitesimal work, and that we are going to calculate during any of the process. And this is we are going to discuss later that this work can be reversible and irreversible, and in thermodynamics we are mostly discussing about reversible work, and reversible works are actually ideal cases of work done, reversible work done. And this has really huge implications or huge usefulness in thermodynamics. So our system can be a gas or a liquid or a solid, and we will see that how can one calculate work done in every situation. So today we are basically going to distinguish between various kinds of processes and the work done related to those processes. So because work done can be achieved with various varying various quantities, so we have given various names to these processes. So if some process is such that we cannot change the volume of the system, we are trying to do some work on the system, but we are unable to change the volume, then such a process is called isochoric or isovolumic process. And the biggest indication of this is that we have to take dW equal to 0 in such kind of a process. So we will encounter, for example, in the last lecture we encountered process like something happened like this. So P diagram. So we had some work like this. So it system went from point A to point B, and you see, if you notice here that during point, if you define a point, for example here a point I here in the middle of the graph, we will see that here from A to I, the change in volume was 0. So this is a kind of process that we can call this curve from A to I is an isochoric process curve. And yesterday we discussed during our discussion session that during an isochoric process the P dV work done is always 0, because for P dV work done we need to have a change in volume somewhere. We will discuss, there would be some cases that we have to determine further properties of this isochoric process, but for the time being we are in a process of defining kinds of processes, 4 processes. So second process is adiabatic process. That is very important process in thermodynamics. We have to use this several times later in the course. So you will learn about this process more and more as the course progresses. And this is the process where we cannot add heat to the system or remove heat from the system. So change in heat, dQ is change in heat, and We can also call this process a process with or process in which the system is thermally insulated. So, for example, you have thermos bottles at your home in which you keep tea or coffee or water, sometimes cold water, and the walls of the thermos bottle are insulating, so no heat can escape or enter into the system. So this process is called as adiabatic process. We will do several examples of this process during our course. Next process is isobaric process. So I told everyone to keep their mics off, but I think the students cannot have some proper sense of what they are doing. I'm terribly sorry that the mics are not off and they are creating nonsense here. Okay, so next process is the process where we have no change in pressure. This kind of process is known as isobaric process, and we will also see several examples. And the one example that we did before was the normal work done example that we did during the last lecture. One node turned off. Okay, I hope you can see my screen even now.
Okay.
Can you see it now?
Yes, sir.
Yes.
Okay. Okay. All right. So isobaric process, PDV example that we did last time, and the last and the very important process is isothermal process. So it's very interesting. In isothermal process, we can add or subtract heat to the system, but we cannot let the temperature change. So temperature of the system should not change. So these are 4 important processes. Normally we will deal with only 2 processes because they occur in nature so often, the adiabatic process and the isothermal process. The isochoric and isobaric process we would not be discussing so much during our next lectures. So now we see how we can see work done during all these processes. So work done during an isochoric process is 0 because change in volume is 0. And for isobaric processes, this is exactly the work done that we discussed before. So nothing special. Now we see examples here that I already showed you yesterday, so I don't need to discuss them again. So now I will calculate work done for an ideal gas for an pure isothermal process, the process for which we cannot let the temperature to change. So the shape of the equation that we will use will always be the same. That would be W is equal to P dV, and because we are using ideal gas equation, so we have to use the ideal gas law equation, PV equals RT. Here we take N equal to 1, the number of moles are 1, so that's why there is no N inside this equation. And because the temperature is constant, so whenever we do integration, this integration from Vi to Vf, we have to take into account that the temperature of the system is constant. And we have to put the value of pressure inside this equation. Okay, just a moment. So we insert the value of P inside this equation, and when we do that, we will get work done equal to, from Vi to Vf, RT over V dV. And from here we know that since R is also a constant, R is a gas constant, it is a number, and temperature is constant from the process, that dT is 0, this because this is isothermal process. So what we do, we just have to integrate over volume. So these two constants come outside the equation, and we just integrate dV over V, and we know from our elementary integration techniques that the integration of 1 over V dV is equal to just log of P, that you already know. And we just have to put limits inside this equation, and when we put limits, then we get at the end of the day an equation that will look like this. So this is the work done for an isothermal process. So you in your problems, in your questions, or in your papers, you might get you have now here 3 variables, no? Work done, final volume, initial volume. These are the 3 variables that you have, and you will get any 2 of them, and you will be asked to calculate the 4th one. So you should do that thing easily. You should be able to do that thing easily. Temperature would be given, everything else would be given, and from these 3 variables, that work done W, Vf and Vi, you will be given 2 of them, and you will be asked to calculate the 3rd one. So this kind of problems you will encounter during this course, and you should remember that this will be the shape. Every time you will be asked to do calculations of work done for an isothermal process, you should keep in mind that you will always use this equation. Okay, the next important concept is heat capacity. Heat capacity is from the name that you are saying, it means something to store. Capacity means to store something. Store. Capacity or capability or whatever you call it. But in thermodynamics, this definition is not this kind of meaning is not valid. So for heat capacity we mean some heat required. The general and in layman terms, for ordinary people, you will say that okay, it is some heat that is required to raise the temperature of a system by 1 degree. 1 degree. 1 degree can be Celsius or Kelvin, but 1 degree is the general definition. So the amount of heat that we need to give to the system to increase its temperature by just 1 degree. And this is a really cool idea, because whenever we give heat to the system, so it increases its temperature by some degree. And sometimes it is 1 degree or maybe 10 degrees, it depends upon amount of heat, but the amount that we give to increase 1 degree, for 1 degree increase, it's always a constant. So this is a material property. So if you define it in a precise way, you will get the idea that you have to for every material it's a fixed number, the amount of heat. So in general it is defined as C. Heat capacity is defined as C, and it is dq over dt. That is this is the definition that you will get in books, but I asked you to remember like this. So it is the amount of heat that you require to increase the temperature. I write it like this initially in the beginning, and then I make it an equation. So this is that is proportional to change the temperature, somehow directly related to change of temperature. This is dq, means the amount of heat, and this is dt, that means this is the increase in temperature or decrease in temperature. If we remove this, then the temperature will decrease. And when we shape it in the form of an equation, then we add a constant to it, and we call it that constant as C dt. So this is how heat capacity is defined. Okay, amount of heat required to increase the temperature. Okay, now in this equation, and there would be another confusion to you that okay, why I'm defining here dq as the heat. So this is heat, not heat capacity. Heat capacity is this C. Oh, sorry, heat. Sorry. Okay, so this is heat, and this is heat capacity. And then from, if you rearrange this equation, you get this equation. Screen show नहीं हो रही?
सर हो रही है शो.
Okay, so सिर्फ एक स्टूडेंट को नहीं शो हो रही. तो एनी हाउ रिकॉर्डिंग आई होप चल रही है हमारी, तो अगर ये होगी रिकॉर्डिंग तो वो शेयर कर देंगे. ओके, सो मैं आपको बता रहा हूँ, अब मैं थोड़ा इसको ज़्यादा सिंप्लीफाई करता हूँ. मेरे ख्याल है कि आप लोग इसको शायद ना कर पा रहे हो. तो हमने डिफाइन किया है वो हीट जो हमें इसका टेम्परेचर इंक्रीज करने के लिए चाहिए, और जब हम इन दोनों चीज़ों की रेशो लेंगे, उस हीट एडिड की और टेम्परेचर चेंज की, तो उसको हम हीट कैपेसिटी कहेंगे. सो the heat we added or removed divided by the temperature it's changed. So that is the ratio of these two quantities that we need to define as heat capacity, or sometimes we define it as or we call it as specific heat. आप लोगों ने थर्मोडायनेमिक्स का कोर्स पढ़ा है, तो उसमें ये चीज़ें मौजूद हैं, पहले भी आपने पढ़ी होंगी. तो ये स्पेसिफिक हीट है. सिर्फ dq जो है वो हीट है, लेकिन जब इसको आप डिवाइड करेंगे dt से, तो देन इट विल बिकम स्पेसिफिक हीट C ऑफ एनी काइंड. अब नॉर्मली ये होता है कि हमारे पास सिस्टम्स जो हैं वो दो तरह से बिहेव करते हैं. या तो एक ऐसा सिस्टम होगा जिसमें सिस्टम का प्रेशर चेंज होगा, वॉल्यूम कांस्टेंट रहेगा, और एक ऐसा प्रोसेस भी हो सकता है जिसमें सिस्टम का वॉल्यूम चेंज हो और प्रेशर कांस्टेंट रहे। तो दोनों तरह के प्रोसेसेस के लिए हीट कैपेसिटी डिफरेंट है। Heat capacity for constant volume process is different. Heat capacity for constant, this is CV, this is the heat capacity for constant volume process. जब भी ये सबस्क्रिप्ट में V लिखा होगा तो that will always mean that that value is a constant. So CV means here volume is constant, volume is not changing. इसको मैं आपको एक्सप्लेन करता हूँ एक मिनट में। Here pressure is constant. Why these two values will be different? So just take an example that you are cooking some food at your home and you are heating it, but you are cooking it in a pressure cooker. What you are doing? You are doing it in a pressure cooker. So can you tell me which condition would be applied to this situation? You can answer, anyone can answer via sound.
CV कंडीशन अप्लाई, कांस्टेंट प्रेशर तो नहीं होगा उसका, लेकिन वॉल्यूम उसका कांस्टेंट ही रहेगा।
Volume constant होगा, तो that would be the pressure cooker situation will deal with the CV thing. Okay, so here the volume of the cooker cannot change. Okay, so it's a fixed thing, but you are adding heat to it, so this will be our first case. The amount of heat that we will require for to add the to increase the temperature would be CV. Specific heat, that would be CV. And if now you are cooking in an open container, in an open pot, so then that would be the case where your volume will be changing. Okay, some things will be evaporated out, and then you are adding heat to increase the temperature. And you can tell from your basic logic where would be more heat required in this case. In which case we will require more heat to increase the temperature. Just tell from your logic.
सर सेकंड केस है जहाँ पे वेपर्स एवेपोरेट हो रहे हैं।
Yes, जब आपको उसमें वेपर्स एवेपोरेट हो रहे हैं और आपका सिस्टम जो है वो उसको एवेपोरेशन के लिए भी एक हीट चाहिए अलहदा से, तो देन उसका टेम्परेचर इंक्रीज करने के लिए उसको ज़्यादा हीट देनी पड़ेगी. सो वन विल रिक्वायर मोर हीट in case of constant pressure. So you can here write for convenience that Cp is always greater than Cv. All right. But there is another small modification that you have to do. This is the this case is always true. Cp is always greater than Cv, but you have to define Cp's and Cv's for fixed amount of the same system. So if you want to heat something, you have to define, okay, I am heating 1 mole of some substance, and then you can compare the values. If you don't divide, if you are taking like 1 kilo of something to heat and then you are taking 2 kilos of something else to heat, then you will always require more heat to heat 2 kilos. Okay, for 1 kg of something you will require less heat to increase its temperature by 1 degree, and for the same thing and 2 kilos of that you will require more heat. So you have to specify for each material that how much you are taking for that system, how much amount of that system you are taking. So in that case, you define molar heat capacities. So you have to define the heat capacity that you defined here, like Cp or Cv, with the moles of that material. And then if you define it that way, so then Cv, that is capital Cv now, and you are dividing it with N here, then it becomes the sign we change for this, and this becomes small Cv, and that is molar specific heat now. Molar specific heat, and that is the thing that everyone uses in literature, in science, in physics, the quantity molar specific heat. Similarly for Cp, if you could divide it with N, then it becomes small Cp, and that is the quantity that we normally use in thermodynamics. Cp, okay. Molar specific heat at constant pressure. And again, the relationship always holds. Cp is always greater than Cv, whether it's molar or normal one. This is the equation. These are the equations for this kind of thing. Here I defined with I wrote with N, so you can also write number of moles with symbol M. It does not matter. So this is how it will be written as. Okay, I move on to next slide, where we are defining stuff. So now we move on to calculate Cp minus Cv. What is the difference, the molar difference between these two? And for that, we will use first law of thermodynamics. dq is equal to du plus p dv. But there is a word of caution that I am using here a small u and small q and small v, which means that we have divided. So we had this equation, dq equals du plus p dv normally, and if we divide with the number of moles and on both sides, then they become molar heat, molar energy per mole, and volume per mole, molar volume, molar energy, and molar heat. So dq over n is now dq small, and du, that was capital U, is now du over n is now small du, and similarly dv over n is now small dv. So it shows they are now molar volume, molar energy, energy per mole, or whatever however you want to call it. So here, this is the first law in terms of molar volumes and molar energies, this guy here. And because energy is a function of temperature and molar volume, that is the functional form. So how you can change energy, whether you increase its temperature or you can change its volume. So that is why it is defined as it is a function of temperature and molar volume. And when something is a function of two variables, as here, we have to take the partial derivatives to define the complete derivative of that thing. So in the second step that you are looking at here, so du is equal to partial, because it's a function of temperature and volume, so you have to define partial derivatives. So to make it as a function of temperature, you define this partial derivative, partial u or partial d times dt, plus, and because it's a function of volume as well, molar volume, then you have to differentiate with respect to volume. So that would be partial u over partial v. And remember that whenever you are taking these kinds of partial derivatives, so you have to take partial derivative with respect to one variable, and the other variable becomes constant. So in this equation, so here this sub u shows that sub v shows that here for this derivative volume is constant. For this partial derivative you have to take volume as constant, and here you take temperature as constant while taking partial derivative with respect to volume. This is the simple explanation. And because now you have partial u or partial v, so you have to put the value from your first law of thermodynamics. So I define this equation as equation 1 here. Okay. क्या आप मुझे सुन रहे हैं? कोई है सुनने वाला या मैं अकेला ही बोल रहा हूँ?
Yes, sir.
Screen भी share
Yes, sir.
Okay. So अब आपको यहाँ पे सब्स्टिट्यूट करनी पड़ेगी वो. Okay. So you have to तो आप ये वैल्यू उठाएंगे, you will take this value of du and put it back into equation 1. So if you define this as equation 2, then put equation 1 into 2, put equation 2 into 1, and then you will get this equation of dq equals partial u or partial t dt and the other values. And because dv have now two things, I can solve in front of you so that you are easy what we have done here. So what is the advantage of this live lecture, that I should calculate everything in front of you so that you can understand. So we have to put equation 2 into 1. So dq now becomes partial u over partial t with v as constant dt plus partial u over partial v dv, and we have plus dv from equation 1 plus p dv from equation 1, this part as it is. Okay, and then just you have to take the things common. Partial u over partial v plus p dv is common from these two. So your equation 1 now becomes equation 3. Okay, I think quite straightforward is that. Okay. Now let's go back to the case where we have defined that for a constant volume process means dV is 0. When dV is 0, capital dV or small dV, both 0, then if you put that into equation 3, put it back in equation 3. So you will get dq equals partial u over partial t dt. So what you get?
partial u over partial
dq equals मैं लिखता हूँ इसको साथ में ही ना, इधर लिखता हूँ. तो आपको मिलेगा dq equals partial u over partial t with v as constant over dt, and you divide this dt on the left hand side, so you get dq over dt equals partial u over partial t with v as constant. And now you know that dq over dt, you have just defined dq over dt. What is that? Just a while ago you defined it. This is your C, heat capacity. And now you are taking which case?
volume constant.
Volume constant. So this is your CV. So this, now you have defined CV in another terms, that is now equal to partial u over partial t. So now you are getting another definition of CV, that is partial u over partial t. Previously it was partial q over partial t or dq over dt, but now it is partial u over partial t, meaning that for constant volume process, your heat capacity will be a differential of internal energy. U is internal energy, no? You know that.
Yes.
U is internal energy. So now it is a differential of internal energy with respect to temperature. There you have another definition. Okay, and now we want to manipulate heat capacity at constant pressure. So we go back to our equation 3 again. This equation I defined before yours, this equation. Okay, and what we do to this equation, we divide both sides with dt. What we do? We divide both sides of equation 3 with dt. I write it on this slide. Divide both sides of equation 3 by dt. So you take a differential with respect to t, or derivative with respect to t, and what will happen, that when you do that, so your you have here dt. I go back, I should have left some spaces to write. Okay, so what will happen here, that your dt will be cancelled by dt, this, so here you will get a dt here, so on this side you get a dt, and this dt and dt will be cancelled, and then you will get a dt underneath this dv here. Okay, understood? So you get one dt here, one dt here, but this, there is already a dt here, that will be cancelled, and you will get at the end of the equation another dt on this, underneath this equation. So what we do here, we just get this equation at the end of the day. That is for constant pressure. We call this equation 4, and now we define from this equation that you have already, from your definition, this is your CV. You just defined a while ago. like 2 minutes ago, you said that this is your CV, first term, and you can define other terms also. The term on your left hand side, this is your CP, because this is the heat you are adding at constant pressure, because there is no term that contains dP here. You don't see anything. So that is the case, and you just simplify and you get Cp equals Cv plus partial U or partial V plus P, and then there is defined something known as dV over dt, and that dV over dt is I have written it as beta. Beta is defined as dV over dt at constant pressure. So this is called compressibility. This is called compressibility. Or volume. No, not compressibility, something else. Anyhow, for the time being, you just remember that it is known as beta. Okay, question?
सर उसके साथ v भी तो है, small v.
V beta है.
V beta, this whole thing is
yes,
V beta.
Sir, V beta.
V beta. My mistake here. Okay, V beta. So V underscore beta. Okay, it's not multiplied beta. It's written like it's multiplied, but it's actually V underscore or subscript beta. So then we can define Cp minus Cv. So we take this Cp on the other side, and then we get Cp minus Cv equal to this. And now I ask you to do some calculations. Use this equation. I call this equation 5 roughly, and you have to use this for an ideal gas, and you need to reach this equation, Cp minus Cv equals R. So can you tell me how you do that? So for you do this for an ideal gas.
Ideal gas sir, ये तो हर वक्त pressure constant है.
Okay, तो कैसे करेंगे फिर? Please answer in your mic.
Ideal gas equation use करके इसका हम इसे constant equal करेंगे.
Okay, and because you have now partial U over partial V also, so you have to define U first.
U तो सब internal energy है ना.
हाँ, उसको कैसे define करेंगे आप? So you may use first law also. Okay, you may also use first law and the ideal gas equation both, and then you should get as a result. So this is like a small assignment, home assignment that you do. Small home assignment for your I will ask you, or if you can, if you do it, then you can share it with us in the next class. Next class means next week. So I just go ahead and discuss now adiabatic process. So adiabatic process, I told you that no heat enters or leaves the system. dQ is 0. So you again revert to your first law of thermodynamics. This is the statement of first law of thermodynamics: dQ equals du plus P dV. And if you put dQ equal to 0 in this equation here, you say that your dq is 0, this thing is 0, then you are left with du equals minus p dv. Then you are left with, this implies that your du equals minus of p dv, and dq you define as du you define as you just defined the dcv as du over dt. So your du will be defined in terms of cv now. That will be du will be equal to cv dt. Okay, and you just separate you just put the value here, cv dt equals minus p dv, and from here you isolate dt, that would be equal to minus p dv over cv. Okay, you understood what I did here? It's easy, no? You just manipulate these equations, first law, and then you put the definition of heat capacity at constant volume, and then you get this equation, dt equals minus p dv over cv. This is pretty straightforward. This easy. Okay, then you are defining adiabatic process for an ideal gas. Please turn your mics off. Who has turned his mic on? Okay. So if you have to ask a question, otherwise keep your mics off, please. Okay. So for an ideal gas, again we use PV is equal to nRT and T is equal to PV over nR, and from here you just differentiate it. You take differential of T using this ideal law, dt equals P dV plus VdP, because this is again product of two variables. So for product you have to take differentials like this. I told you even yesterday that the differential of PV equals P del PV plus VdP. So that you did here, and you have from the previous slide you have the value of dt, that is minus p dv over cv, and then you just put it here. You can call it equation, this equation as equation 6 or 7, whatever the number is. So this is your equation 6, and you put the value of dt from equation 6 into equation 7. I call this equation 7. So you have to deal with a lot of equations, so just number them, and then you put 6 into 7. Simple. And you get for adiabatic process a rough equation like this. You can call it 8, roughly, doing things roughly. And what you do next, is that, because this is an adiabatic process, you have to rearrange this equation to get some meaningful things out of it. So this is the rearrangement. You are doing various rearrangements here. Rearranging, more rearranging. I am not doing these steps. You do this at home. This is all rearrangements of the same equation. Rearrange equation 8, and then you get this thing here, and at the end of the day you will get, and then you put values actually. So nr plus cv is from your equation Cp minus Cv is equal to nr. So there is a relationship here. So you are rearranging stuff on this slide, and on next slide when you reach here you put Cp minus Cv is equal to nr, then nr plus Cv would be equal to Cp. So you get this. And do I need to do these rearrangements in front of you, or you will do it? Tell me just now.
सर कर लेंगे सर.
सर कर लेंगे, अगर ना हुआ तो पूछ लेंगे. यस सर.
Okay, because I can do it in front of you and then it will take a bit of time. Simple है, इसमें कुछ ज़्यादा तो है नहीं. आपको नज़र आ ही रहा होगा कि इसमें कुछ बहुत ज़्यादा चीज़ें तो नहीं चल रही. जस्ट जहाँ पे मैं कुछ मुश्किल है वो आपको समझा दी है कि यहाँ पे आपने nr प्लस cv की जगह cp पुट करना है, and you will be getting this equation, and then you have to define something new here. This is the definition gamma. Gamma is the definition of Cp और Cv, और ये फिक्स्ड होती है हर मटेरियल के लिए. तो जब आप गैमा इसमें पुट करेंगे, फिलहाल तो आप इसको जस्ट गैमा ही ट्रीट करें, आपको ये इक्वेशन मिल जाएगी गैमा पी डी वी प्लस वी डी पी इक्वल 0, और इसको आप सेपरेट करेंगे. यहाँ पे आप नेक्स्ट स्लाइड में, ओके मैं नेक्स्ट स्लाइड नहीं होती, तो नेक्स्ट स्लाइड में आपने यहाँ पे आपने किया है, जहाँ पे इस इक्वेशन को आपने सेपरेशन ऑफ वेरिएबल्स किया है. सेपरेशन ऑफ वेरिएबल्स, दैट मीन्स कि आपके dv वाली टर्म्स अलग कर ली हैं आपने और dp वाली अलग कर ली हैं. ये करना क्यों ज़रूरी है कि जब हम इनको इंटीग्रेट करेंगे इस इक्वेशन को, तो तब हमारे पास चीज़ें सिंप्लीफाइड फॉर्म में होंगी. तो अब dv इस पे आप इंटीग्रेट करेंगे, ये लिखा हुआ है साथ इंटीग्रेटेड, तो dv ओवर v आ जाएगा log ऑफ v, और dp ओवर dp आ जाएगा log ऑफ p, और राइट हैंड साइड चूँकि 0 थी इसकी, तो वो हो जाएगी कांस्टेंट. 0 को आप इंटीग्रेट करेंगे तो आपको कोई कांस्टेंट मिलेगा यहाँ पे, तो आप जस्ट लिख देंगे जस्ट कांस्टेंट, और फिर आप इनको फर्दर रीअरेंज करेंगे. आपको पता है कि log के साथ कोई चीज़ मल्टीप्लाई हो रही हो तो वो उसकी पावर हो जाती है बाद में. तो नेक्स्ट स्टेप में आपने देखा कि गैमा log ऑफ v इज़ नाउ log ऑफ v टू द पावर गैमा. ठीक हो गया. अब आपके यहाँ पे जब ये इक्वेशन आ जाएगी log ऑफ v टू द पावर गैमा प्लस log ऑफ p, तो यहाँ पे आपके पास ये डेफिनेशन यूज होगी कि log ऑफ a प्लस log ऑफ b इज इक्वल टू log ऑफ ab. दो चीज़ें log में ऐड हो रही हूँ तो वो मल्टीप्लाई हो जाती हैं. तो ये चीज़ आपने यहाँ पे यूज़ की नेक्स्ट में, और यहाँ पे आपके पास एक नेट रिजल्ट आ चुका है pv गैमा इज अ कांस्टेंट. नॉर्मली आपके पास रिजल्ट हुआ करता है pv इज इक्वल टू nRT. ये होता है आपके पास फॉर नॉर्मल आइसोथर्मल प्रोसेस, आप कह लें इसको. लेकिन एडियाबैटिक के लिए जब आपने कैलकुलेशंस की dq0 के लिए, जो आपने पिछली 2-3 स्लाइड्स में की हैं, तो आपके पास एक और तरह की इक्वेशन आ गई है, वो जो कि इसके बराबर नहीं है. pv इज इक्वल आइसोथर्मल में t कांस्टेंट होगा ना, तो ये सारी चीज़ कांस्टेंट हो जाएगी इधर. तो pv इज इक्वल टू कांस्टेंट, जबकि एडियाबैटिक में ऐसा नहीं है, बल्कि pv के ऊपर एक और चीज़ ऐड हुई है, दैट इज़ गैमा v टू द पावर गैमा, एक चीज़ ऐड हुई है. तो अब कोई बता सकता है कि इन दोनों में क्या डिफरेंस होगा एट द एंड ऑफ द डे? कैन एनी स्टूडेंट टेल मी ऑन योर वॉइस कि ये दोनों इक्वेशंस क्या बता रही हैं हमें नेट रिजल्ट के तौर पे? कि एक कैलकुलेशन हमने की ए डायबिटिक प्रोसेस के लिए, दिस इज फॉर ए डायबिटिक प्रोसेस, और ये हमारे पास है आइसोथर्मल के लिए. So please answer someone. Hello. कोई है मौजूद?
यस सर।
सर आपकी स्क्रीन ही नजर आ रही।
स्क्रीन तो चलो नजर आ जाएगी, ये बताएं ये क्या हुआ है? सबको नहीं नजर आ रही मेरी स्क्रीन?
यस सर।
यस सर और नो
ब्लैक हो गई है।
ओके
यस सर, नजर नहीं आ रही।
ओके, मैं दोबारा शेयर कर देता हूँ, कोई मसला नहीं है वो। अब बताएं।
सर अब हो रही है।
ये कितनी देर से गायब हुई थी?
सर अभी 2 मिनट में, 2 मिनट भी नहीं, 1 मिनट हुआ था बस, थोड़ी देर।
अच्छा अच्छा, आप बताएं जी इन दोनों में क्या फ़र्क होगा, कुछ मुझे एक्सप्लेन कर सकते हैं थोड़ा सा? PV गैमा इज इक्वल टू कांस्टेंट और PV इज इक्वल टू कांस्टेंट। आप स्क्रीन पे लिखी हुई दोनों चीज़ें। मुझे आवाज़ नहीं सुनाई दे रही किसी की भी।
सर एडियाबैटिक में प्रेशर तेजी से फॉल करेगा आई थिंक, क्योंकि इसके ऊपर पावर है गैमा, एक्सपोनेंशियल डिक्रीज होगा इसका एज
अच्छा
कंपेयर टू आइसोथर्मल।
ओके, और कोई? एनीवन एल्स? लेक्चर बोरिंग है बट इतना भी नहीं कि आप लोग खामोशी हो जाएं। कोई है जवाब देने वाला? कोई गैस ही लगाओ, ये ठीक कुछ बात करने की कोशिश की है आपने, लेकिन अभी इसको थोड़ा सा और हमने देखना है कि क्या है, क्या सकता है ये।
सर आइसोथर्मल में एक्चुअली हमने कहा था ना कि जो प्रेशर कांस्टेंट नहीं है, तो इस वजह से, जबकि एडियाबैटिक में हमने ये कंडीशन लगाई थी कि प्रेशर जो है वो हमारा कांस्टेंट है।
हाँ हाँ
उसमें जो टेम्परेचर का इंक्रीज है एडियाबैटिक में वो भी बहुत तेजी से होना चाहिए, अब पता नहीं है कि नहीं। और आइसोथर्मल में एज कम्पेयर टू स्लो होना चाहिए, क्योंकि इसमें हमने प्रेशर कांस्टेंट नहीं रखा, मतलब प्रेशर कांस्टेंट नहीं रखा हुआ, तो ज्यादातर एनर्जी जो सी है वो यूटिलाइज हो जाएगी काइनेटिक एनर्जी ऑफ द पार्टिकल में,
ओके।
तो टेम्परेचर उतना
ये
तेजी
तो
से
वो
इंक्रीज नहीं
बातें
करेगा उसका।
हैं जो कि थोड़ी सी क्या है, थोड़ी सी आइडियल सी हैं। एक सिंपल इसका अगर आप लोगों से पूछा जाए तो कुछ गेस कर सकते हैं कि नहीं? अगर मैं इन दोनों को प्लॉट करूं किसी PV डायग्राम के ऊपर, दोनों को PV इज इक्वल टू कांस्टेंट को और PV इज इक्वल टू गैमा, इसको ये कांस्टेंट हो, तो इसको अगर मैं प्लॉट करूं तो कोई उसका 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 कोई रिलेशनशिप समझ आता है आपको?
सो वो गैमा की वजह से तेजी से डिक्रीज करेगा ना, क्योंकि उसके ऊपर पावर गैमा है,
अच्छा
एक्सपोनेंशियल डिक्रीज उसका ज्यादा होगा। और दूसरे के ऊपर जो इनसे पी वी इज इक्वल टू एन आर टी है, मतलब वी के ऊपर कोई पावर नहीं है, तो वो उसका जो डिक्रीज होगा आई थिंक फिर वो लीनियर होना चाहिए, बिकॉज मतलब उतना तेजी से नहीं होगा जितना दूसरे का होगा, पी वी की पावर जिसके ऊपर गैमा है।
अच्छा ठीक है, तो दूसरे लफ्जों में आप क्या बता रहे हैं कि ये स्लोप किसी की फर्क होगी, तो इस तरह की बात है?
यस सर,
तो किसकी ज्यादा होगी?
एक्सपोनेंशियल डिक्रीज एक का ज्यादा होगा, एक का कम होगा। तो गैमा वाले का ज्यादा होगा एक्सपोनेंशियल डिक्रीज और दूसरे वाले का कम होगा।